Hello. So far in these lectures, as far as I think, you learned about the general concepts and ideas of the Newtonian physics. You developed the Newton's laws of physics, you know about them. So you think that given a number of particles, let's say you are given a number of particles and you know the forces acting on these particles, and let's say you are also given the initial conditions of the systems, well, you can think that, well, I can solve the system exactly, so why worry? Well, the thing is that the systems can be very complicated, and it's not always very straightforward and easy to solve the Newton's laws of physics, given that you have a very complicated systems and particles are interacting with each other. So it's always useful to know about a system without knowing the details of the system. Maybe a physical system has some global valid properties that doesn't require you to investigate the details of the system. So that's today's topic. Today we would like to understand how systems behave just because Newton's laws of physics are true. We are not going to investigate the details of the systems, okay? We are not worried about the details of the systems. We will just investigate some physical quantities, some physical systems by just assuming that the Newton's laws of physics hold. So let's start simple. Let's start with a very simple problem. I have this baseball, and the problem is that I would like to apply some force on it, and I'm wondering, like, what happens when I apply force on this baseball? Well, it's obvious. I don't care what kind of force I apply, but I know by Newton's laws of physics that as long as I apply a force on this, well, this thing will accelerate, right? F equal to ma. So this thing will accelerate. Acceleration means the change in speed, so I know that if I apply a force on this baseball, it will either speed up or speed down, I don't know what it is, but it will accelerate, so the speed will change, so its initial speed or initial speed and the final speed will be different, okay? So I know that F equal to ma, which tells me that if I apply a force on a baseball, then definitely the baseball will accelerate. Now this force can be any kind of force. This acceleration can be three-dimensional, two-dimensional, I don't know. But let's start investigating this system in the simplest setting. Let's say I have this baseball and I'm investigating the motion of this baseball in a one-dimensional line. Okay, so I apply a force on the baseball in this one-dimensional line, and I start applying the force at this point. Let's say this is the point x equal to a, and this is the point x equal to b. So I apply the force on this baseball, start applying at x equal to a, and I apply the force until I reach the x equal to b. Well, what happens? Well, what's going to happen is that the baseball will accelerate, thereby its velocity at x equal to a will be different than x equal to b. Okay, so first thing first, I would like to quantify this velocity change. Since the force is just one-dimensional, and since it's a constant force, so I'm thinking about the simplest setting, it's a constant force, thereby the acceleration is constant. So if the acceleration is constant, which is given by F divided by m, well, the velocity of my baseball at given time is simply given by its initial velocity plus a times t, and the position of the baseball at any time is given by x0 plus v0t plus a half a t square. Well, a is f divided by m, so I can use this equation, let's say this is equation number 1. I can use the equation number 1 to solve t in terms of v0 and f and m. So t is simply 1 over a, which is m divided by f times v minus v0. Then I can plug this t in this equation, let's say equation number 2, which tells me that x minus x0 is simply v0 times t, so it's v0 times m divided by f, v minus v0, plus a half a t square, and a is f divided by m, times the t square is m square divided by f square times v minus v0 square. So if I just do this calculation, then what I get is simply m divided by 2f v square minus v0 square, or in other words, what I get is f times x minus x0 is a half m v square minus a half m v0 square. As expected, I apply a force on the baseball from x0 to x, and what happened was that its velocity or its speed changed. So this quantity is what we call work. So I do some work to take the particle from x0 to x, and this quantity here is called the kinetic energy. which is just 1/2 mv square. Thereby, this quantity is the change of kinetic energy. So if I do some work to take a particle from A to B, then what happens is that its kinetic energy changes. And this is what we call the Work-Energy Theorem. Okay, let's think about a simple example. For instance, I have this baseball right here. Let's think about a constant force, for example, let's say gravity. So I know gravity here is approximately m times g, it's almost constant. And what I would like to do is that I would like to take this baseball from this point, and I would like to take it to that point, okay? So there is a difference in height. And I let gravity do it. So I have a baseball here. The baseball is located at x equal to, let's say, a. And what I would like to do is that I would like to take the baseball to this location, which is x equal to b, and I will let gravity do it, okay? So this is my baseball, and there's a force on it. So let's say this is the y direction. So the force on the baseball is simply minus mg times j hat. And let's say the distance between A and B is simply h. So what I know is that at initial time at t equal to 0, my baseball is here, and I give it an initial velocity, okay? So its velocity is something like v0, and it's in the upwards direction. It's a v0 in y direction. And I let gravity do work. Gravity is in opposite direction. Therefore, my baseball will accelerate in this direction. So this velocity, v0, will go smaller and smaller and smaller. And at some point, which I expect that this point is x equal to b, it will be 0. So I will take, so by using gravity, I'll take my baseball from x equal to a to x equal to b. So at here, let's say xb, and that's just vb is just 0. So how much work gravity does? Or in other words, what initial velocity should I give so that the gravity takes the baseball from x equal to a to x equal to b? Well, that's simple. The work that's done by gravity is mg times the change in distance. So it's mg times h. Is the change in the velocity, so it is 1/2 mvb square minus 1/2 mva square. Well, vb is 0, that's the final speed, and the final speed is 0. So the initial speed, va, which is what I call v0, I can solve it, so I can eliminate m's, and the v0 square is simply nothing but 2g times h. So if I give this amount of initial velocity and I let gravity do work, I'll take my baseball from xa to xb. Let's now think about the following example. So I have this baseball right here, okay? And the net amount of force on this baseball is obviously 0 because it's not accelerating. So the gravity applies some force, it's m times g, which means that I also apply some force, which is plus mg. So the gravity applies minus mg if this is my y direction, like so. So I apply plus mg, and the gravity applies minus mg. So let's say I take this baseball from this location, and I take it up here, okay? So obviously, the initial velocity is 0, the final velocity is 0. That means the net amount of work that's done on this baseball must be 0. So as we just calculated, the work that's done by gravity is mg times h, is minus mgh. I take the baseball from x equal to a to x equal to b. The distance between a and b is h. So the gravity did minus mgh amount of work, which means that I did plus mgh amount of work. By the way, before I proceed, as you see, the unit of work here, the unit of work is simply the unit of force times the unit of length, which is Newton times meters, which is what we call joule. So now we investigated a one-dimensional system that's derived by a constant force, and we found something that we call a work-energy theorem, which states that if I take a system from a point A to point B, the work that I do on the system, or work that's done by a force on the system, is simply the change in kinetic energy. As promised, this has nothing to do with the details of the system. I never said that what kind of force derives this system, right? For instance, I could take the baseball and I could just put some charge on the baseball and I can apply an electric field, and the electric field can just derive this baseball from a point A to point B. Or in the previous example, I can let gravity do it. It doesn't matter. This has nothing to do with the details of the system. It doesn't care about the details of the system. It just doesn't care about what kind of force derives. It just cares about where the system started, where the system ended, and what was the initial velocity and what was the final velocity. As I promised, this is independent of the details of the system. But you might say that, okay, but this is a one-dimensional problem, and you just considered a constant force. Let's deviate from this. Let's consider the simplest deviation. So the simplest deviation would be that let's think about, again, a one-dimensional problem, but let's say the force now can change from one position to another position. So now I will take F to be an f of x. Okay? I will let force to change from one position to another position. So I'm still interested in one-dimensional problem. Okay, so I still take my baseball, let's say, from A to B, or some system from A to B, and I apply a force on it. I apply a force on my baseball. So there's a force here, F, which is f of x. Now what I can do here is that I can divide this line from A to B into infinitesimal segments, such that their lengths are just dx. And I know that whatever f is, it's x dependent, and I'm going to assume that this is a smooth function. Okay, that means that over this distance, f will be constant. So the amount of the work that I have to do to take the particle from here to there, just the delta x piece of displacement, the amount of work that I have to do is simply f times dx. Because f can stay constant on this infinitesimal segment because it's a smooth function. Which tells me that then the total amount of work that I have to do to take the particle from A to B is simply the integral from A to B f dot dx. Well, f is ma, or in other words, it's dv divided by dt. And dx, I can write this down as v dt, which tells me that I can eliminate dt's, so that the work I have to do is simply mv dv. Okay, so this is just a one-dimensional problem, and clearly this just tells me that it's a 1/2 mvb square minus a half mva square. So as in the one-dimensional case with a constant velocity, nothing changed. The work that I have to do to take the particle from A to B is still given by the change of kinetic energy. Okay, let's now take it to another level. So I'll make it even a bit more complicated. Now I will take the varying force, and I'll consider a three-dimensional case. Now, before thinking about the three-dimensional case, let me take this chair here, and we think about three-dimensional case before we proceed. So I am going to apply some force on this chair, and I'll take it from this point A to here, point B. Okay? In order to do that, I'll apply a force. Let's first apply a force that's parallel to this path. So I apply a force in x direction. Let's say this is my positive x direction. So I apply a force in this direction, and that's fine. But that's just the one-dimensional problem that we just sorted out. What I can do instead is that I can do a different force. Let's say I apply a force like this. Now my force has two components. One is in y direction, and the other is in x direction. And I apply a force like that, but it still goes in x direction. So which means that the force that I apply in y direction doesn't do any work. So it doesn't mean that just because you apply a force on something, you do work on the system. So you can consider also this one. You see I'm sitting on it, okay? It's not going anywhere. Its velocity is not changing. Obviously, the force that I apply on this chair is not doing any work on the chair. So when I think about the three-dimensional cases, I have to be careful about the force and the displacement. So let's say I now have a particle and I move it from A to B, like so, and let's say this is a three-dimensional plane. So I do it by applying a force. Let's say I apply a force like this here, I apply a different force here, I apply a different force here. But obviously not all components of this force does work to take the particle from A to B. Only the one that's parallel to the displacement does work. Let's say this is dl. Okay? Only the parallel that's to this displacement does work, like so, right? I'm applying a force on it in both x and y direction, but only the x part, the x component of the force does work on displacement of this chair. And the mathematical operator that does that for you is what you call a dot product. So the work that you have to do to take the particle from A to B is simply now given by F dot dr. So the force, if the force is perpendicular to the displacement, then that means the force doesn't do any work, like so, right? Now I'm applying a force on the chair, I don't do any work. It's not going anywhere, its velocity is not changing, I don't do any work. Only the force that is parallel to the displacement does work. So you say that, okay, let's evaluate this. And you wonder whether the work-energy theorem still holds. Well, let's see. So F is simply, in 3 dimensions, I can write this down as Fx I hat plus Fy j hat plus Fz k hat. And dr, your displacement, or dl in this case, is simply dx I hat, dy j hat, and dz k hat. And if I plug it in, what I get is ax fx dx plus fy dy plus fz dz. It's just a dot product. The boundaries are then ax bx, ay by, and az bz. So this is the integral that I just evaluated. So I decompose a 3-dimensional problem into 3 one-dimensional problems. And the result is obvious. Then this will just give me the change in velocities in x direction, change in the velocities in the y direction, change in the velocities in the z direction, or in terms of the vectors, it will simply tell me that this is vb square minus half m va square, where v, the vector v, is simply vx I hat, vy j hat, and vz k hat. So we just learned that nothing changes. You can think about a one-dimensional problem with a constant force. You can think about a one-dimensional problem with a varying force. You can think about a 3-dimensional problem with a varying force. The work-energy theorem always holds. Every time you have to do some work on the system in order to change its velocity from point B to point A. Now, as an example, I will consider a one-dimensional example with a changing varying force. So for that, I will take a spring and a mass system. So I have a spring, and there's a mass attached to it. I'm going to attach the mass in a second. So this is the relaxed length of my spring. So I will call this x equal to 0. So if I have to attach a mass at the end of the string, and if I stretch it or if I squeeze it, the spring applies a force on the mass. And this force is in the direction such that it just calls the particle, calls the mass back to the equilibrium. So if I just take it and stretch it in this direction, let's say I stretch it to here, then the spring applies a force on the mass, and the force that it applies is given by simply minus kx, where minus comes from the fact that the spring calls the mass back to the equilibrium position. And this is what we call the Hooke's law. So let's consider such a system. Obviously, the force that's applied by the spring is position dependent, thereby it changes from one location to another location. For instance, if I stretch it too much, or if I stretch it like here, it applies k times x, and if I just take it to here, it applies some other k times x, but since this x is greater than that x, the force changes, and force depends on the position. So what I do here is that I just take this from the equilibrium position and bring it here, okay? So you see that the initial velocity is 0 and the final velocity is 0. So the net amount of work that's done on the space ball is just simply 0 because the change in kinetic energy is 0. So apparently then the amount of work that's done by myself is minus the work that's done by the spring. So now I would like to know how much work have I done to take the baseball from the equilibrium position to right here, let's say x, some x, let's say this is x. Well, that's simple to calculate. I can just calculate that's work done by the spring, and I can take the minus of it. So the work done by the spring, well, spring is taking this baseball from x equal to 0 to some x, and the force that it applies is minus times kx, so it's just minus kx dx, which gives rise to minus a half kx squared. So that's the work that's done by the spring, which means that the work that's done by me, that's my initials, and this is a half k times x squared. So if I am taking the baseball from some xa to xb, the work that I do is simply 1/2 kxb squared minus a half kxa squared. Now let's say I stretch this to a position, let's say this is x max. So the work that I must do, or let's say I stretch it and it's at x equal to x max, and I just let it go now. Now when I let it go, what happens is that, well, there's a force acting on my baseball, thereby it will start accelerating to this direction, okay? And the change in velocity is simply then given by the work that's done by the spring to take it from xa to some arbitrary x, or x max to some arbitrary x. Therefore, the work that's done by the spring is simply 1/2 kx max squared minus a half kx squared is simply the change in velocity, but I just let it go from x max, which means that its initial velocity is 0. So it will just pick up some velocity depending on the position, which is then given by a half mvt squared. You can now determine the velocity at any position depending on the position and the maximal position. So let's now find out what's the velocity at x equal to 0, let's say the equilibrium position. So I let it go, I let go the baseball, and the force is pulling, the spring is pulling the baseball towards the minus x direction, and at some point it will just pass through x equal to x0, and now I would like to calculate the velocity of the baseball while it is passing from x equal to x0. So for that I have x equal to 0, which means that Vx equal to 0. So I have 1/2 kx max squared is a half Vx equal to 0 squared, which simply tells me that Vx equal to 0 squared is nothing but k over mx max squared. Now we have seen the Work-Energy Theorem, and Work-Energy Theorem, as you hopefully noticed, that it's a very peculiar theorem. It just tells you that the work that's done by yourself or by some force on a system is just equal to the change in kinetic energy, which means that what we only care about is that where the system started, which velocity it started, where it ended, and with which velocity it ended. Okay, so it only cares about how you start and how it ends, and it doesn't care about what happens in between. That's something very peculiar, and that's something very funny. And in the following lectures, I will teach you about something called also potential energy, and this is very similar. Potential energy will also only care about where you start and where you end, and it will not care about what happens in between. And together with potential energy and the kinetic energy, I'll define you something called the mechanical energy. And by using the mechanical energy, we will be able to understand very complicated systems without caring about the details of the systems. We will only care about how the system started, with which velocity and which position, and how it ended. And just these initial and final configurations will tell us a lot about the systems without worrying about its detail.